Hello everyone, welcome to the joint demonstration from AWS, Infineon, and Klika Tech of ready-to-use HVAC predictive maintenance kit. I'm joined today by two of my co-presenters, Manuel Hohlfelder from Infineon Technologies and Andrew Mazur from Klika Tech. In the following 20 minutes, Manuel will explain the benefits of the approach they've chosen and also show the modular design of the hardware. Then Andrew will go through the design and show the solution in action. Needless to say how important clean, fresh air to our health and comfortable environmental setting to our productivity. It is also can be safety critical in a data centers, labs, industrial setting, office buildings, and conference venues. I'm not sure about other countries, but in the US, in many municipalities, HVAC and PTAC units are highly regulated, and you cannot simply replace the units with a newer model or different vendors. We actually experienced this working with a couple of customers in New York City. Extensive reference design from Infineon allows you equally well build new smart HVAC model or retrofit existing unit with a ready-to-use reference hardware design and complete backend developed using AWS Edge and cloud services. Notably, FreeRTOS and our communication libraries on a microcontroller board and AWS IoT Core, Kinesis, Lambda, Elasticsearch in the cloud. Without further ado, let me pass the word to Manuel, who will explain the business case and the approach they took for the extensive, and also show us the modular design of this kit. Manuel?
Thank you very much, Anton, for the warm introduction, and I'd like to take over to present you our extensive predictive maintenance evaluation kit, which we jointly developed with AWS and Klika Tech. First of all, I'd like to tell you more about predictive maintenance. Predictive maintenance is a data-driven maintenance scheme, and it monitors the system condition to predict when a device fails and what type of failure might occur. If predictive maintenance schemes are applied to HVAC systems, as an example inside buildings, it helps to avoid up to 70% of breakdowns, cuts maintenance costs by up to 25%, and ensures a longer equipment lifetime of up to 20%. So what does it take to truly implement predictive maintenance at scale for HVAC systems inside buildings? First of all, as you see here, there is not a single expertise which you need to truly implement predictive maintenance, but rather different fields of expertise are required. As an example, first of all, you require sensor expertise, as you need to select the right kind of sensors to capture the most critical data of your system. Based on this data captured by sensors, you require data analytics expertise to get the right insights from the data. To put this all together, of course, software expertise is required if you would like to implement it at the edge. But also, if you'd like to analyze this data at scale, cloud expertise is required to truly implement an end-to-end solution for predictive maintenance. As explained, we require multiple levels and fields of expertise to truly implement predictive maintenance and condition monitoring for HVAC equipment. To provide you an out-of-the-box experience for predictive maintenance, we at Infineon decided to partner up along the IoT value chain to provide you ease of use for applying and installing sensors, as an example, at HVAC equipment, getting data out of the sensor and analyzing it, but also sending it to the cloud for further analysis. This is the reason why we at Infineon decided to partner up with cloud experts from AWS, but also the IoT experts from Klika Tech to provide end-to-end implementation of such a solution. We would like to show you now the extensive predictive maintenance evaluation kit and what it consists of. First of all, we have a main board which hosts an XMC 4700 microcontroller, which is part of Infineon's XMC microcontroller family. The XMC 4700 is an ARM Cortex-M4 microcontroller with a floating point unit, and due to its highly specialized peripherals, especially well suited for industrial applications like motor control or switch mode power supply. On top of this main board, we provide a mainboard extension shield, as you see on the right. The red board is the main board and the green board on top is the mainboard extension shield. The mainboard extension shield provides you a variety of connectivity like Wi-Fi and Bluetooth, and the possibility to further extend it with a narrowband IoT LTE click shield on top of it. You see also additional RJ45 checks here, which are used to be connected to up to 7 satellite boards. Here, these checks provide you differential signal and provide you the possibility to connect sensor boards via industrial rugged interfaces. As an example, we convert the single-ended I2C to differential mode to provide it along the standard twisted pair cabling so that you can run this interface up to multiple meters of cable length. On the other side, we have up to 7 satellite boards which convert the differential signaling back to single-ended mode. To these 7 satellite boards, you can connect highly specialized sensor boards which are provided as up to 13 satellite sensor boards. As an example, what you see from the picture, we show you our highly sensitive barometric pressure sensor, which allow you to measure tiny pressure changes, which is connected on the right side to a satellite board. On the other hand, we also provide the possibility, as an example via I2S, to connect our digital MEMS microphone to a satellite board before you go in differential mode to the mainboard extension shield. We also provide additional sensors like our magnetic current sensors, our Hall sensors, or also our 3D magnetic sensor for vibration and position monitoring. Together with the hardware and sensors, we provide all software, both on the embedded and cloud side, and documentation to allow you a quick and easy bring up of the overall solution. Moreover, you will get also all needed cables like the power supply, the USB cables, and also all connectors to get the full out-of-box experience, and also to get the full experience of quickly setting everything up, getting the sensor data, transferring it securely to the cloud, and storing it there. Also, cloud provisioning and enrollment is easily done as we provide an Optica Trust M, which is a hardware security solution from Infineon. This security turnkey solution provides you zero-touch provisioning and AWS multi-account registration, so that you also can easily enroll this kit in the field, authenticate it, and bring it up so that it securely can send data to the AWS cloud. Thanks to data analytics and software processing, we enable you to get additional insights from these raw sensor values. As an example, let's take our highly sensitive parametric pressure sensor DPS368. From pressure measurements, you are able to calculate airflow rate and can implement airflow monitoring with the DPS368. This allows you, as an example, to detect clogged filters and also decide when to change the filter. Thanks to our highly sensitive MEMS microphone, you are able to implement noise monitoring and sound anomaly detection, which helps you to detect upcoming failures, as an example, inside motors or compressors. Thanks to our magnetic current sensor, you are able to capture current values inside your HVAC equipment. On top of these current values, as an example, you can implement, thanks to data analytics, current anomaly detection. This current anomaly detection allows you to derive from strange values inside the current flow predictions about ongoing failures of the compressor, motor, or other kind of equipment. We are also implementing and using our 3D magnetic sensor, which allow you to implement vibration and position monitoring. Also here, we use our linear Hall sensor to implement linear vibration measurement. This is quite new and novel in the field, as typically used for such kind of applications accelerometers. Here, we get, thanks to the 3D magnetic sensor, direct information from the spatial room from which we can predict and detect vibration patterns. Moreover, we also use our Hall sensors to implement open and closed lid detection, but also speed and direction measurement with our double Hall sensor. All in all, you see that based on sensor insights and sensor values, you are able to implement higher level of abstraction and get additional insights on system level, which allow you to implement truly predictive maintenance and condition monitoring. Before we will give you a real-life demonstration, I'd like to give you a short summary what you have seen so far and what we presented to you. First of all, Condition monitoring and predictive maintenance are key features in enabling smarter HVAC devices to increase uptime and reduce costs. Together with our partners, Infineon developed an evaluation kit for easy and quick evaluation of condition monitoring and predictive maintenance features in HVAC systems. This extensive predictive maintenance evaluation kit comes with all necessary hardware, software, and documentation. And by partnering with AWS and Klika Tech, Infineon can provide full end-to-end support in your predictive maintenance design journey. And with this, I'd like to hand over to Andrew, who is going to show you a demonstrator. Andrew, the stage is yours.
Hi Manuel, thank you. So today we'll see in action extensive predictive maintenance evaluation kit. With its help, we'll monitor the current state of the portable HVAC unit. And moreover, we will emulate an unexpected behavior of this HVAC device to demonstrate you that the system can detect anomalies. But before we start, let me please share with you an architecture diagram. As you can see, there are several core components. First of all, we have a portable HVAC unit. Then we have extensive predictive maintenance evaluation kit that is attached to the HVAC unit. We have an AWS-based cloud solution for data processing, and we also have a data visualization application. As you can see, the raw data is collected from the sensors that are attached to the HVAC and processed on the edge with the help of Infineon XMC4700 that is powered by the FreeRTOS, a real-time operating system. Later, this data is wrapped into the MQTT messages and sent to the cloud. AWS IoT Core is the main data ingest service for IoT devices. It has an MQTT broker that accepts all the incoming messages. Later on, AWS IoT Rules service propagates the incoming data to all the other AWS services. Amazon Kinesis Data Analytics provides an online anomaly detection module. It is based on the random cut forest algorithm. It is an unsupervised algorithm for detecting anomalous data points within a specific dataset. The anomaly score is then stored in the Amazon Elasticsearch service using the Amazon Kinesis Data Firehouse service. And later on, the Amazon Elasticsearch service provides a search and analytics capabilities that are useful for building a live visual representation of the data. And then this prepared data is visualized in the Kibana dashboard. It is the tool that we use for visualizing the data for the end user. Moving to the dashboard. Here you will see the data that is coming from the sensors that are attached to the HVAC unit. We'll monitor the current state of the HVAC device, and we'll take a sensors data coming from temperature sensors, from pressure sensors, from current sensors, and also from the microphone and Hall sensors that we attach to the HVAC body. So let's move to the top two graphs. As you can see, one on the left visualizes the anomaly score that is calculated at the moment. The right top graph shows the time series data of anomaly scores. When the values on the both graphs are in a green zone, the HVAC behaves as expected. On the other hand, when the data is visualized in the green zone, that something went wrong and anomaly has been detected. Okay, let's move to our demonstrator. It is a portable HVAC unit that has been chosen only for the demonstration purposes due to its mobility. It has the same structure as other HVAC devices. Within the demonstrator, we monitor the compressor, air exchange fans. Here is the compressor, and here, in just a second, we'll see the first output fan, and here is the other. Okay, so let's move on. Here is the main board extension shield that is attached to the main board. It aggregates all the sensors data that are connected to it, and it runs FreeRTOS, real-time operating system. So we have attached several current sensors. One is used to measure the current consumed by the compressor, and the other two sensors for measuring the current consumed by the output fans, both cold and hot. When the average consumed current changes significantly, it means that something went wrong with the motor, or a filter and a compressor should be changed. So here we can see one of the temperature sensors. It is used to measure the compressor body temperature, which should be in an acceptable range. If not, then the compressor should be considered near to fail. Another two sensors are used to measure the air temperature coming out of fans, both cold and hot. In case the cooling system works fine, it shows the value around 0 for a cold outlet and more than 40 degrees Celsius for the hot outlet. This sensor has an outstanding characteristic in measuring pressure. As the fans blow, it increases the pressure on the sensors relatively to the atmospheric one. So it could be compared and checked whether the fan air is blowing or not. We have also attached a linear Hall sensor. Here it is. It is attached near to the compressor body, but has no mechanical connection with it. It is an analog sensor, which is used to sense magnetic fields, which vibrate because of the compressor vibration. The spectrum of its signal is pretty clean when the compressor works fine, and as expected, and could be dirty and full of harmonics in case problems such as unscrewed nut or a bearing break. Okay, let's move on. Here you can see the microphone. It is a high dynamic range microphone that is used to record sound inside the HVAC body. The sound spectrum analysis helps to detect many failures before HVAC will stop working. It should be noted that unfortunately usage of the microphones inside the device could be prohibited. Let's move to the demo. Today we'll show you the compressor animal behavior and a fan animal behavior. We'll start with the fan animal behavior. As you can see, the system operates as expected, and we see a green zone in animal score. Now we emulated the dirty filter and closed the fan with an obstacle. As you can see, almost in real time, the hot outlet temperature increases, and all the other temperatures also start increasing. And we see that anomaly has been detected. So the anomaly score is in the red zone right now. A few seconds later, after we removed an obstacle, we'll see that the system will change its behavior and it will cool down a bit, and we'll see that now it operates as expected. In a second, we'll move to yet another demo. Here it is. It's a compressor animal behavior demo. And at the beginning, the HVAC unit operates as expected. We have also connected a heating element to it, to the compressor power circuit supply. It is on the table in a blue color. Now we've switched it on, and you can see that the random cut forced algorithm identified the anomaly. Now we're switching off the heating element, and you'll see that almost instantly the system started behaving as expected. So that were the two demos that we planned to show today. And being that said, I would like to hand over back to Anton.
Thank you, Andrew. I hope this was an informative session for you. I should mention that it's a collective project, and credit goes to many engineers in AWS, Infineon, and Klika Tech working tirelessly to make this kit a reality. From AWS, I want to call out David and Brintha from our IMEA team. Now the action is yours. You can obtain the kit and see how easy to add intelligence in your existing equipment. Please do not hesitate to reach out if you have additional questions. Thank you for your attention. Goodbye.